We are live. Good evening, everyone. Good evening, Swift Cairo. Welcome to a new webinar of Swift Cairo series. Every month, we will have a new webinar. This webinar, we have Saba. We will talk about modern concurrency. I know we talked before about modern concurrency, but we will try talk in deep about this. And yeah, I know there is this time there is a match between Real Madrid and Barcelona. I hope you are watching us or you can watch the recorded and leave any question anytime and we will have a QA session at the end. Welcome Saba. It's really pleasure to have you to Soft Cairo.
Yeah. Hi, Mohammed. Thank you for inviting me for this fifth Cairo meetup. I'm really excited to be present here.
Yeah, thank you so much. I think we can start and I will let you introduce yourself. And
Yeah,
yeah, floor is yours.
sure.
Okay, the presentation is already displayed, so you can start.
Yeah, sure. Yeah. So, yeah, sure. Hope. Yeah. Hello, Mohammed.
Yeah, I will be on the stage watching and write notes about the questions. Okay,
Yeah, okay.
so
Okay.
feel free. I already watched it and feel free to represent and start the presentation.
Okay. Thank you. Um, yeah. Good evening, everyone, and thank you. Um, Thank you, Mohammed, for giving me an exciting opportunity in this fifth Cairo meetup. Today, I'm going to speak building confidence with Swift 6.2 concurrency. I am Kanagasabapathy Rajkumar, and today we are going to turn Swift concurrency from something scary to something you can actually use. Today, I will show you how Swift 6.2 makes concurrency actually approachable. By the end, you will have some confidence to start your migration. But before we dive into the Swift 6.2, let me introduce myself. I am Kanagasabapathy Rajkumar. As it's a long name, feel free to call me Sabha or Sabapathy. I'm an Apple platforms developer with a special focus on two things. Especially the first one is concurrency, which is what we are here to talk about today. And second, Swift package management, because when we are migrating to Swift 6.2, your dependencies matter a lot. I'm also a co-organizer of Swift Bengaluru, our local community in India, and I co-authored Swift published blogs and also podcast host in the YouTube channel. Yeah. So let's. You can find my QR code, LinkedIn, social media. So you will get most of value from this talk. If you are migrating an iOS application from Swift 5.1, 5. Any version to Swift 6, and you are wondering where to even start. You are already tried and now you have sendable compiler errors everywhere. You are confused about main actor and when to use. You have heard about the Swift 6.2 approachable concurrency features and want to understand what that actually means. Or you are just looking for the practical patterns that actually work in real code bases. But if even one of those resonates, you are definitely in the right place. So before that, I would like to ask some questions. Have you ever tried Swift 6, or you are still working with this old version Swift 5? And another question, like, how many of you tried migration, and how many of you tried have got the sendable errors, and you are dealing with this? So these are the three questions I would like to ask each and everyone who participate here in this session. Yeah, let's focus on the concurrency journey. In Swift 5.5, we built it. Apple introduced async await actors and structured concurrency. The community was excited. Finally, modern concurrency in Swift. But the reality hit. Swift 6.0, nobody can migrate. Teams tried to adapt it. They enabled the complete concurrency checking, and suddenly thousands of errors appeared. Projects got stuck. Third-party libraries weren't ready. Migration path was too steep. So Apple listened to the community feedback, and now we got the Swift 6.2 in 2025 approachable concurrency. Apple has introduced the five major concurrency features, each with its own Swift evolution proposals. Async await, readable asynchronous code, no more callbacks, no more cobble hills. And structure concurrency, we have the task with proper life cycles and cancellation, and also parallelism, such as async-let. And we have actors, thread safe objects that protect their own state. And we have a sendable way to mark the types as safe to share across the concurrency boundaries. Async sequence is something like asynchronous iteration, and it's like a sequence but async, and it's a kind of replacement of combine. And now you can see the data race safety at the compile time only. So promise was huge, but the data race safety at the compile time, and technically these features were brilliant, but there was one critical problem. We can check this example. At the time the sendable was optional, we have a simple counter variable. The two tasks are modifying it concurrently. This is a textbook data race. Two threads accessing the same memory, at least one writing, no synchronization. In Swift 5.5, the compiler would say this might cause a data races with a warning symbol. But here is the critical part: it's a warning, not an error. So what we developers do, we ignore the warning. We had deadlines. We shipped the build, and the app shipped with the data races. Sometimes it would crash. Sometimes the counter would go wrong. Sometimes it worked fine. This is the fundamental problem. Optional safety isn't a safety at all. So these are the pain points I would like to tell from the real developers. Someone has my project had 2000 sendable warnings, and then third party libraries don't adapt the sendable protocol, and sometimes pre concurrency doesn't work for the binary frameworks, and the migration is blocked by the slowest library. The pattern was clear. Teams wanted to adapt the Swift concurrency, but the ecosystem wasn't ready. This feedback was crucial. It's what led to the changes in the Swift 6. Swift 6 is the complete concurrency checking. It has a breaking changes, and it has a Swift 6 language mod, and the goal is complete data safety. No more optional warnings, no more ignoring problems. If your code could have a data race, it wouldn't compile. So this was the technically the right decision. Safety should never be optional, but the transition, that's where the things got complicated. So you can check this example. The three fundamental changes. Before Swift 6, we had a sendable as a warning. Now it throws an errors. And in terms of isolation, it was optional. Now it has been required. It is much required. And then main actor, it was implicitly connected. Now it is explicitly we have to do. So before there were zero errors. After adding this, we have 1247 some kind of errors. Yeah, this is fine because that's how it felt. Your code base went from compiling perfectly to completely broken. Now these weren't new bugs; they were existing data races the compiler could finally see. So in software engineering, we have this concept called trilemma. You can only pick two out of three. For Swift concurrency, the three goals were completely safety, the no data races guaranteed by the compiler, and then source compatibility. Existing code keeps working without changes. Incremental migration, you can adapt features gradually. Here is the hard truth: you can't have all three. So if you want complete safety and compatibility, you can't migrate the incrementally. If you want compatibility and incremental, migration, you can't have complete safety, which was in Swift 5.5. If you want safety and incremental migration, you have to break the compatibility, which is Swift 6. Apple had to choose, and they chose the safety. Yeah. So here in Swift 5.5, they chose compatibility and migration. So warnings you could ignore. That is unsafe. So they made a sendable checking optional, just warnings. The result warnings you could ignore equals unsafe code. The teams adapted async await for the nice syntax, but they didn't fix the underlying data races. But there were no forcing function, no requirement to fix them. This is why Swift 6 had to break the changes. In Swift 6, they chose safety plus migration. In the result, breaking changes is nothing necessary pain. Safety was non-negotiable, and data races had to be got in the compile time. Migration was still important. You could adapt module by module, but source compatibility this had to go. The result, breaking changes were necessary pain. Your code would break, and you have to fix it. But once you fixed it, you have guaranteed the data race safety. This was the right long-term decision, but the short-term pain was real. It was the blocking the adaptation. Yes, Swift 6 is technically correct, but too hard to migrate. Yeah, the compile is right. The data races or the catches are real. The safety guarantees are valuable. But if nobody can migrate, what is the point of it? So this is the problem Swift 6.2 solves. Not by compromising on the safety, but by making the path to safety more gradual. By providing better defaults, by reducing the number of annotation you need, by making the error messages clearer. So this was the evolution of from Swift 5.5 to Swift 6. Now compilers supports from Swift 4 and data race safety, and everything should be sendable, and actors should strictly not first in first out. It's kind of a re-entrant. Yeah, on March 2025, Apple announces Swift 6.2. The headline feature is approachable concurrency. This isn't about adding new features, it's about making the existing features easier to adapt. It's about providing a smoother migration path, and it's about learning from the Swift 6 experience. And the most importantly, it's about making concurrency something you can actually use in production. The goal is to make Swift 6 concurrency approachable for the real world projects. This came directly from the community feedback. From those forum posts we saw earlier, from the team struggling with the migration, from library authors trying to support their users, the initiative has several components, but they all share one philosophy: start simple, add complexity only when needed. So you can see the key proposals of the Swift 6.2. First, you can see the async functions inherit isolation. This is huge. We will dive into later. And 0470 isolated protocol conformances, making the protocols work better with the actors. And if you see 472 task immediate for sync context, that bridge the gap between the sync and async. So earlier we had a task detached that will go in an independent way, and task will be go in async way, and now immediate that's in a sync context. Task naming for debugging. We all know concurrency. We are unable to debug the concurrency main actor, how it goes, and what are the hangs. So we are unable to find out the task also. So finally, we got the readable task names in the instruments, and in the task priority escalation that prevents the priority inversion issues. They aren't just issues; they are solutions to the real problems team faced. So this diagram shows their journey from Swift 5.5. We had a async await, the new features, optional safety, and then we have a complete concurrency checking, complete safety, but breaking changes. And now we got the Swift 6.2 practical adoption and approachable defaults. We have gone from this great to this impossible and to okay, this is actually works. That's approachable concurrency. Approachable concurrency, this is a philosophy, and we have a certain features. Main actor by default, that is a default actor isolation. Your code starts on main thread, and we have a concurrent attribute explicitly run on the background work. And if you have a lot of computation work, you can go with the concurrent attribute. And we have a sending keyword, that is really helpful for smarter ownership transfer across the concurrency boundaries. But here is the key insight. Swift 6.2 inverts the model. So instead of opt out from the concurrency, you have to opt in to the concurrency when you need it. This is a psychologically and practically better. So when you enable the approachable concurrency in Swift 6, you are actually enabling these two upcoming features: non-isolated, non-sending by default. The functions are non-isolated unless you say otherwise. And infer isolated conformance, that is for protocol conformances. To the compiler infers actor isolation for the protocol conformances. These two flags change the default behavior. Instead of everything being isolated, things are non-isolated by default. You add isolation when you need it. And this shows the complexity of backporting to Swift 5. So you will need to enable 5 separate features along with the non-isolated, non-sending by default, and infer isolated conformances. We have infer sendable from the captures, and that makes closure smarter about the sendable, and followed with the disable outward actor interference that prevents unwanted actor interference inference. And we have a global actor isolated types usability that makes global actors more useful. And the good news is that if you are on Swift 6, you will have to only two, and if you are in still in Swift 5, you will have to you add five more thing. And the better news, if you are starting from the fresh with 6.2, then it's even simpler. So sendable, you might have heard about the sendable closures. We often use it in the closures, and still we are using implicitly using in the objective-c. And also here we have the sending parameter. Let's find the differences between these two. So here you can see the process image that has the parameter of image, and it's a async method. And we have the task. um, the UA, you can see the error, like before that um, the processed, it is assigned to image dot apply filter. It's a UA image. So UA image is not a sendable. We all know that sendable, the UA kit types are not sendable, so it can't capture in the sendable quotient. So the so here we have got the sending parameter that really helpful for this ownership transferring the ownership. So here we can't use the image here anymore. The ownership was already transferred to the process. So here the sendable closures type can be copied across the boundaries is safely, but sending the values moves across the boundaries ownership transfer. So here is a decision tree, you can take a look. So initially you need to pass a value across the isolation boundaries. This is the initial check, and if it is a type is a thread safe, and you can make it make that conformable to the sendable protocol. If it is not, and you find that is a closure or a function type, you can use it as a sendable attribute, that is a sendable closure. If it is not, you can transfer the ownership by using the sending keyword. If not, you can redesign or use unchecked sendable, but be careful while using the unchecked sendable. So it prone to get errors in the production. Next, we have got the sendable meta type protocol It's a new in Swift 6.2. It's a part of SE0470 Swift evolution proposal. And this protocol exists to solve a specific problem with the isolated conformances. Before we see the solution, let's take a look at the problem, how it solves. And it's an advanced topic, but still, if you are fine with this problem, you can refer. So you can see the my model that conforms to the main actor isolated. That is a main actor isolated, and it's conformed to the equitable protocol. Generally, equitable protocol that will have the static function, and here this static function also a main actor isolated. So you can't conform to the non-isolated protocol. So equitable is non-isolated protocol. So equitable requires the static function, uh, and you can look at the error that's a main actor isolated. So the problem is equitable is not a isolated, but our class is main actor isolated. The compiler doesn't know it's whether it's a safe to compare these across the isolation boundaries. This breaks a lot of common patterns. So you can't use your main actor types in the sets, dictionaries, or a generic algorithms. So look at the difference. So here we have added the main actor, and now equitable that confirms the it's a main actor isolated as well. So now the conformance is isolated to the main actor. So this means this static function runs on the main actor. So both sides of the comparison are guaranteed to be on the main actor. The conformance is safe because it respects the isolation. This can be a game changer by using the actors with the protocols. You can have isolated equitable or a hashable or a codable. So this is an actual definition. It's an empty protocol. Sendable meta type is an empty protocol. And if you see the sendable, that conforms to the sendable meta type protocol. So then sendable inherits from it. So why the extra layer to separate the concerns? Sendable meta type is about the meta type, that type itself. Sendable is about instances of the type. This lets the compiler reason about the isolated conformances. It's a technical detail you rarely interact with directly. What does it mean in practice? If you have a main actor equitable conformance, you can't use it where sendable is required. Generic functions with where like t that confirms a generic function like t has a sendable that won't accept it. This is by design. Isolated conformances aren't safe to send across the boundaries. It's a trade-off. You get the protocol conformance, but with limitations. So this is the actual build setting in the Xcode. You can see the one checkbox that's approachable concurrency. If you enable the approachable concurrency, you don't need to remember all these flag names that I have mentioned earlier. If you check in, you will be able to configure easily. This is available in Xcode 26 version, so you can take a look at this and notice that how Apple made it simple, like one setting, not 5 flags to configure. You can manually, if you set no, then it will change to no. And if you don't want specific one, you can set manually. So this is a combined approachable concurrency set of all flags that comes under the approachable concurrency. So we have a default actor isolation. So here you can select the two options, like determine, like you don't want specify any actor or something. You have two choices. One is non-isolated, that code runs whatever, no actor isolation. Main actor, that code defaults to running on the main thread. For iOS applications with UI, main actor is usually the best choice. So this is a safe by default approach. Your UI code stays on the main thread unless you explicitly move it off. Let's see the explicitly move it off in the upcoming the slides. And so this is the settings you can configure. So we can enable the main actor. If you want to change to non-isolated, then it will become a non-isolated. So you take a note of this Swift evolution proposal 0466, the default actor isolation inference. So if you go to the Swift evolution proposal, you will find out the lot of examples also. So that will guide you more better. I have taken some of the examples from the Swift evolution. So before Swift 6.2, you can see we have to add everywhere the main actor. You need to repeat again and again, even for class, property, function. It's a kind of repetitive and easy to forget, and also verbose for the heavy UI applications, especially Swift UI or UI Kit. So after we have the Swift 6.2, by using this default actor isolation, you can set in the build settings or compiler flags. Swift module automatically assumes all top level declarations are on main actor. No need to manually annotate everything. Compiler automatically protects your code under main actor. Now, now this is another choice. Like you can also choose the non-isolated here. So for server side Swift or some other networking, those things you can probably go with the non-isolated. That makes more sense. And I repeat again that safe by default approach. Your code, if you want to go with the main actor, your code stays on the main thread unless you explicitly move it off. So you can take look at this approachable concurrency and the default actor isolation. So we have three different functions like normal function and non-isolated function, and we have a concurrent. This we will go through in the upcoming slides. But before that, you just take a note of this one. So when you set the approachable concurrency as no and default actor isolation as a non-isolated, so it would become in the background thread. When it comes to approachable concurrency S and default actor isolation, that is a non-isolated, then the non-isolated and normal function will become a main. It will run on the main thread, and the concurrent function will always run on the background thread. In case of approachable concurrency S and default actor isolation main actor, then the both these methods will run on the main thread, and the by default concurrent attribute that will run on the background thread. And the final approachable concurrency no and default actor isolation, that's the main actor, then the normal function will run on the main thread, and the other two non-isolated and concurrent attribute will run on the background thread. So so this gives you the predictive behavior and explicit control. This most important proposal. This is a single most important proposal in Swift 6.2 and SE 0461. Yeah. So it changes how async functions inherit their execution context. So before SE 0461, async function would hop to the background thread. It moved to the background thread instead of the main thread, even though it is a main actor isolated. After SE0461, this proposal async function stay on the callers actor. What are the callers actor? It will, if it is a main actor isolated, it will run on the main actor isolated. If it is a non-isolated, then it will run on the non-isolated. If it is a global actor, it will run on the global actor. So this one change eliminates thousands of the main actor isolations, and it makes the code behavior match develop the intuition. And we will see in a real example and of the problem first, and how we are solving, and what were the workarounds we had earlier. So you take this example. This is a problem we had before the Swift 6.2. So you can see it's a main actor isolated, and you can see this refresh content. It is running under the task. So generally it will be in the background, it will be in the background thread. And you can see we have a async method, load remote data. And you are applying the data to UI in the task itself, that not guaranteed on main actor. And before that, you can see this line of code that hops off the main actor from the main. It runs on the background thread, and it produces in delay. Like, the await that creates a suspension point. Let other things work on it. So you will get like incorrect results, and also you can't apply the data to the UI. So, and also it's not guaranteed on the main actor, and or main thread. So before I show the workarounds people were using, like, I want to hear from you. So what did you do when you had the main actor issues? What hacks did you come up with? Any guesses? So I would like to go with my workarounds. So this became the go-to solution for many developers. The idea is simple: wrap your UI updates in the main actor run. Closure follows with the closure, and it's explicit. It works, but as we all see in a moment, it has a problems. But here is the thing: it's a workaround, not a solution. So you can check this piece of code. You are having the await keyword and followed with the main actor dot run, and followed the closure, and we are applying the data to UI. So this is the pattern we have: await main actor dot run followed by a closure. Inside the closure we call our UI update function. It works because main actor dot run explicitly moves execution to the main thread. But notice what we are doing here: we are manually managing what should be automatic. Every time you fetch data and need to update UI, you write this wrapper. It's like manually shifting gears in a car that should have an automatic transmission. And the keyword goes before function that's nothing like non-isolated. This function is marked as a non-isolated, which means it doesn't inherit the main actor isolation. In Swift 6.0, without non-isolated, this async function would be confusing. With non-isolated, we are being explicit, and this function doesn't care about the actors, what color actors we have. It can be called from anywhere and run on whatever thread it wants. This is actually what Swift 6.2 will do will do automatically for you in many cases. But before 6.2, you had to write it explicitly every time. We have another workaround. You can separate or segregate this load remote data on the async method that has the uh, that will return a data in actor. So if you go with a separate actor, and that also considered as a workaround, and it serves our purpose. But these are the workarounds, not the complete solution. So you might come across the feature flag: non-isolated, non-sending by default. This is one of these names that make you go, what? Non-isolated, we just learned that. Non-sending, about not sending the data across isolation boundaries. By default, this becomes the default behavior. In Swift 6, you could enable this flag to get the Swift 6.2 behavior early. It's like a beta feature that become a standard. If you're migrating from Swift 6 to 6.2, you might see this in build settings. I have already shown you earlier in the compiler flag, and also in the Xcode settings. Yeah, this would be the example, and we have got the solution. The same example I have chosen. The non-isolated async function now run on the caller actors by default. Nothing, callers actors is main actor by default. So you don't need to add the main actor everywhere. So this will remains on the main actor. And you can see the non-isolated function. and this will be safe access on the main actor. So everything will be running on the main actor, so we don't need to worry about this. So this is the magic of the SE0461. The await doesn't leave the main actor. Then we call apply data to UI, also with the check mark, because we never left main actor. UI updates are safe. No main actor dot run followed with the closure wrappers, or no manual synchronization, or no separate actor. So you can find the QR code, and you can check the full proposal if you want to dive deep. So this is the foundation of the approachable concurrency. Then the one we have earlier discussed in the difference of functions, like normal functions and non-isolated and concurrent. So how it works in the approachable concurrency and also default actor isolation based on the selection. So this is a brand new in the Swift 6.2. It's a way to explicitly say that this function should run concurrently. Unlike non-isolated, which opts out of the isolation, this concurrent attribute that opts into the concurrent behavior. Think of it as an opposite approach to the same problem. Instead of removing the protection, you are adding a specific concurrent capabilities. And let's see what it looks in the code. And you can see add concurrent to the function requires background processing. You can take the background processing network thing, or any huge that huge computation that will take, so you can make use of the concurrent. Yeah, so we have a main actor isolated view model, and you can see the concurrent that's a new in 6.2, and you are having the load remote data. Earlier in the example we were using the non-isolated, that will comes out of the isolation domain. So instead we can go with the concurrent attribute. So even though we are in the main actor class, the function runs off the main thread. It's a perfectly for the heavy work that you never want on the main thread. Image processing, data parsing, or file operations, all are great examples. The caller on main actor can await this safely. When it returns, you are back on the main actor automatically. So this is the new change in the Swift 6.2. You can make use of this concurrent attribute safely, instead of going with the workarounds like main actor dot run followed with this closure, or a non-isolated or a separate actor. And we have gone through the non-isolated, that will come under the actor. It will not go in the main actor, it will consider in the actor. And non-isolated sending, that will be coming in the caller. It can be a main actor or whatever. And concurrent, it will always go in the background thread. These are the differences between these three. So everything I have shown you so far is true and helpful, but there is a cost we need to discuss. It's the kind of thing that shows up in the production, not in the demos. Some of you with large code bases have probably already encountered these things. Let's talk what can go wrong when async functions stay on the main thread, main actor. So look at this code. A main actor, a view model is a main actor isolated with a process data function. Inside this, we have await heavy work. Imagine this is a expensive computation. In Swift 6, without any special attributes, the heavy work can run on the background thread, and then you upgrade to Swift 6.2, enabling the approachable concurrency. Now the heavy work inherits the main actor isolation because it's not isolated by default. Your expensive work moved from background to main thread. So no compiler error, no warning, just was exam or was performance. So this is what the silent regression means. The compiler doesn't tell you. This is one of the good example. And followed with this, you can see The best example, this is a data manager, that is a main actor isolated, and you can see the fetch menu async function, and inside that you have the task group, the structure concurrency, and we have the for loop. So you can see we are adding the task one by one and using the fetch one method that has the suspension point. So each like each task calls the await self fetch one, all 100 run on the main thread, and you try to parallelize work, but this uh, this AC is 0461 that serializes it. So all 100 tasks queue up on the main actor waiting their return. Instead of running concurrently, they run sequentially. So your parallel code become a like serial one. And again, no compiler error. It compiles fine, runs fine, just slow. Yeah, everyone pulling on the same rope at the same time. That's exactly what happens when 100 tasks try to use the main actor simultaneously. They are competing for same single threaded resource. In theory, parallel execution, multiple workers. In reality, a queue, one worker, everyone else are waiting. This visual really captures the problem. So modern hardware has multiple cores. Use them, and we were ignoring the cooperative cancellation earlier. So in the next example, I will show you how to um, like improve the code in terms of the structure concurrency, especially the task. So here you can add the specific thing like you can have this task that check cancellation check before your work, and task groups without cancellation cannot be stopped, and common production bug like long running task group that block the app termination. This demonstrates the Swift's cooperative cancellation model. And in the initial I have shown you this Swift evolution proposal. This is nothing but the task naming. Earlier we used to have the anonymous task in the instruments tool. Now after Swift 6.2, we were able to name those tasks for easy debugging, and you can see the task followed with the name, and you can have it. If not, like you can have a context like image download, you can have the image ID. That will be helpful for checking the debugging tool, and also in the crash logs or OS log messages. This is the completely a new change, and this will help you to understand the we can able to track the task easily in the debugging, and also find out in the instruments easily. So these are the available one Xcode debugger, as you know, and also you can easily find out in the crash logs. Yeah. So we all know the data race and race condition. So a lot of the developers conflate these two terms. Swift 6 prevent the data races, memory safety violations, but Swift 6 does not prevent the race condition, the logical timing issues. Data race. What is the data race? Two two threads accessing the same memory without synchronization. Then what about race condition? The current synchronization happen, but unexpected order of execution the operation. The Swift's type system catches the data races at compile time easily, but the race condition or logic bugs, no compiler can catch those. So I will explain you the difference between the race data race and the race condition. So you have an actor like a saved counter. It has a value of 0, and we have an increment function which has the value incrementing by 1. And you can see the task that detached, that is calling in the save counter. You can see we are calling the counter increment method using the task dot digit. We all know the task dot digit is that will execute independently, in not in the same thread. It will independently execute in the different thread. So here the value, like both in increments happen on the same order, but never simultaneously. In the older Swift, we were using the class without actors. You could get 0, 1, 2. That is a data race. The value could be corrupted by simultaneous access. That is a data race and memory corruption from the concurrent access. So Swift 6 actors that prevent this completely. The type system won't tell you to write unsafe concurrent memory access. But in the same time, like Swift 6 does not prevent the race condition. This is crucial to understand. The Swift 6 that prevents the data race but not the race condition. So look at this example actor that has a balance of 1000, and you have the withdraw function that has a three steps. One is we are checking the balance, you should be greater than the amount, and we have a suspension point we are calling the log method, and that is a async method. Some async work is there, so we are using the suspension point, that is await keyword, and followed with the balance we are calculating and reducing the amount based on the act. Yeah. So here is the problem between the check and the act. There is an await. So await means other task can run. So two withdrawals of 600 could both pass the check. Then both subtract 600, leaving you with like minus negative balance. The memory is safe, like no data race, but the logic is wrong. This is a classic check then act race condition, and Swift type system can't catch this. This is a logic bug. So this is a cheat sheet, I would say, that you can take a screenshot. And we have earlier discussed about the overloading the main actor. So the fix you can we have already discussed. We can use the non-isolated or a concurrent. And if you see the hidden actor reentrancy, generally the actor reentrancy is a feature. So instead of the serial actors, we can go with that reentrance. So that's why Swift has given you the actor reentrant. But there is a fix like capture state before await. That's a this fix you can able to solve the actor reentrancy problem. And the long running task never yield. So you can use the task yield with the suspension point, ignoring the cooperative cancellation. So you must use the task dot check cancellation method, and misusing the sendable. Based on the context you need to choose it. And we have already discussed about the task dot detached, so that will run on the independently in the different thread, so that gives you incorrect results. So always use the structured task. And for synchronization you can go with the task dot immediate that we have discussed. And in one of the proposal they have added this task dot immediate, and but that has some disadvantage also, that it depends on the depends on the features you are going to apply. So as we discussed, that Swift 6 that guarantees no data race. The memory corruption from the concurrent access is impossible. Second, the sendable types can be shared across the boundaries safely. And the third one is actors that protect the state from the concurrent access. And followed with the isolation, it's checked at the compile time, no runtime surprises. So these are the compiler enforced guarantees. If your if your code compiles in the Swift 6, these are the true. This is huge. Most languages can't make these promises. But what we have seen in what we can't guarantee in Swift 6 is race conditions, the no bugs in logic. Sometimes some developers want actors should be serial instead of reentrance. So that creates a reentrancy bug. So, but when you compare with the dispatch queue earlier we had in the GCD, I think the actors reentrant is a feature, not a problem. We have to handle it well, and you can see the performance is optimal. Like you check the main actor usage, if you put everything in the main actor the performance will be low. and we have already discussed about the Swift SE0461 proposal. Yeah, these are the things I have tried in my network kit. I was trying to migrate something from using the approachable concurrency. You can check these are the errors I was getting. So this was the only deep codable earlier. So method can't be declared public because its result use an internal type. And another one is that capture of non-sendable t dot t type is an isolated closure. So these were the fix I could see here. This is the old code, and we are able to fix it. Now I'm able to build it. So I need to update uh, my Swift package manager library, so that we can use it. Use the network layer in each and every project, so it handles better. Since we have the approachable concurrency and also the default actor isolation can be possible in the Swift package manager also. So this is a narrative arc we have been following. In Swift 5.5 we built it, no enforcement. So no, and there is no restrictive. We have got some unsafe code, and the compiler would not stop you, and you got the warnings instead of the errors. And then Act 2 is nothing like Swift 6 that has been introduced in 2024, that we enforce it. That is too strict. Correct code was hard to write. Developers had to give up. So we had a solution now. The correct path to easy path, safety without the pain. Now we make it approachable in Swift 6.2. So yeah, this is why we are here today. Swift 6.2 is the resolution of this story. It's the version where concurrency finally feels natural. So these are the things we have discussed earlier. The approachable concurrency, make correct code, the easy code, and followed with this 0461. We have talked about the how async function inherit the caller isolation, convenient but requires active and non-isolated, and we have found some hidden cost also. So we have some solutions also, and earlier we had a workarounds before introducing this fifth evolution. And yeah, sendable meta type, that is a new protocol that has been introduced in this Swift 6.2, that prevents isolated conformance from leaking. Earlier the protocols were not working well with the actors, so they have introduced this option, sendable meta type protocol. Actor reentrancy, like I told, that is by design, that enables process, but we need to capture the state before await that. Otherwise it will create an suspension point and it will go out. The other task will run, and then the actor reentrant problem will be there. And also we have discussed about the differences between the data raise and the raise condition. Swift 6 that prevents the first, not the later. And we have a pre-concurrency. We If you have a legacy code, we have to use this pre-concurrency, and that is a migration escape hatch. So these are the things. So this is your mental model for the Swift 6.2 concurrency. Safety first, convenience second, but both are possible. The compiler is your ally. Trust it, learn it, work with it. So you can find my socials. I hope this talk has helped you to learn something about the Swift 6.2 concurrency. We have covered a lot, from the history to the hidden patterns, and this is my contact information. You can find my LinkedIn, and you can follow me on the Twitter, and also you can find my podcast recordings. And also we have discussed with the several Swift developers, iOS developers, and feel free to reach with me with the questions. And remember that Swift concurrency is approachable now. Don't be afraid to adapt it. The compiler has your back. So thank you for the opportunity.
Yeah, thank you so much, Sava, for this great, interesting topic. I really like it. The arrangement starting from ideas related to proposals until the hidden gems. So yeah, I will ask you to have a demo about this with the presentation. I will so we can share it with maybe from the network kit or something like this.
Yeah,
Starting from yeah, I'm here.
I will share the demo after. I will record and send you to you, and you can post it on the YouTube.
Yeah.
So,
Thanks so
so
much.
currently, yeah, currently I
Yeah,
have Swift package management. So I will execute in the separate project,
yeah.
and
I
I will
think
do
you
it.
can share it on your own GitHub, and we can share this link
Yeah,
with demo. It will be totally fine.
yeah.
Um, yeah, thanks so much for again for having you in this webinar. I really like it, and yeah,
Thank you.
honestly I don't have any questions because you already covered everything, starting from the idea, from proposals. You already, I think we can share the links of these proposals. You already
Yeah,
mentioned numbers on it. You can search, everyone can search on it on the GitHub on Swift repo.
yeah.
And yeah, thanks so much. And
Thank you.
I really enjoyed, and have a nice day.
Thank you,
Thank
Mohammed,
you,
for the
so
time.
thank you.
And
Thank
yeah,
you all, and waiting
thank
you
you.
for a new activity or new webinar next month. Thank you.
Yeah, sure. Thank you.